next presenter is Bjorn Vaagansmith. He's going to present his work in visualization for cyber-physical state awareness of distribution grid. Dr. Vaagansmith received his master and PhD degrees in electrical engineering with an emphasis on electronic materials and devices from South Dakota State University. Currently, he's working as an electrical engineering researcher at Idaho National Lab, where he has over 4 years of experience in building and working with customized power system data acquisition solutions, as well as performing various power system studies.
Thank you, Jairo, for the introduction, and thank you to the University of Utah for hosting me down here, and also for the collaboration on this project. Another acknowledgement to the Virginia Commonwealth University, who also contributed to this work, as well as a lot of the other colleagues at INL, who mostly did this work. I helped to oversee it. I didn't actually do the actual work. So just as an outline for what I'll be discussing, this is primarily related to our collaboration with the University of Utah with the Solar Starts project. And so I'll be giving a brief introduction and then just kind of giving you a little bit of a tour around all the different tools that we developed to help increase situational awareness via collaboration between the cyber defender and the power engineer through visualization systems. So in the power grid paradigm, the collaboration is quite constrained between the cyber defender and power grid operators. Usually it's limited to a phone call. So if there's problems going on the power grid, if there's a cyber physical attack occurring, the power grid operators are not aware of the cyber element, and they're reliant on the cyber defenders to either pick up the phone, or in a worst case, they actually have to physically leave their office and then try and go into the operator's location to warn them, hey, we think there's some cyber anomalous activity. So the communication there is optimal, and that really limits the situational awareness on things. If you have a cyber attack on the grid that's causing a physical problem, just simply going out to fix the physical problem will not remove the fundamental problem that's causing that on the grid. So for this project, the Solar Starts, we developed 4 different tools, essentially, and different visualization methods of displaying those tools, with the goal of creating a common interface that the power grid operators and the cyber defenders could use, and that would serve as kind of like a common basis for them to be able to communicate with one another. And then trying to minimize the amount of crossover information. Right now, the cyber defenders and the power grid operators in their own respective domains, they have to deal with overwhelming amounts of data that is constantly being fed to them as they manage very large systems. So increasing any amount of data that they have to look is usually a no-go for them. Additionally, they're usually not very well versed in each other's disciplines. So the cyber defender doesn't really know how the power grid works, and the power grid operator is usually not very well versed in current up-to-date cybersecurity practices. So we wanted to respect those different domains and not blend the information together so much, and with the strategy we took on. So moving forward, I'll just begin to talk about some of the different tools that we used that will be a common basis for communication between cyber defenders and power engineers. And that is the INSTAR method. Let's see if I can't get my cursor over here. So I like using the cursor to point, so you'll have to deal with that, I guess. So the INSTAR method, which gives the physical health of the system. The PSI-STAR method, which is detection of the cyber anomaly. And then the resilience metrics, and then how all these come together in the visualization of these tools. So the INSTAR metric, it is a deviation-based health assessment of your power grid. It has 2 main functions here. It has the alpha and the beta function. If I can get a pointer here. There we go. So there we are. So the alpha and the beta function, it talks about how, or it describes how much the bus voltage or the power flow deviates from what would be normally expected. And then these would feed into a lambda value, which summarizes basically what's the health of either a single bus or an aggregation of different components. It's mostly up to the user to decide how they define that. And then that is fed, and that's going to provide you a local health assessment, and that is fed into further computations, which consider a dependency factor that takes into account if one aggregation of components is dependent on another. So, for example, if power flow has to go through one aggregation or one section of the grid to reach another, that one section would be dependent on it. So it takes into account these dependencies, takes into account that lambda local health, and if there's any local generation that can be leveraged, so there's a supply factor. Another thing that can be done is if this lambda is representative of a critical load, such as a hospital or something, you can also weight it heavier than other areas that are a little bit less important. So in that way, you can more accurately reflect what are the priorities of the grid operators as far as keeping parts of the grid up. Then these all come together similar to how a feed-forward neural network works. We actually had some machine learning guys design this metric for us, and then it will compute a global health metric. And these lambda and this global health metric calculation, they are values between 0 and 1. The next tool that we developed is the SciStar metric, which is a cyber sensor. It takes in packet data. It looks at where the source of this data came from and the destination of where it's going. And that can help with determining, where the source of an attack comes if some anomalous. It also does a little bit of deep packet inspection to look at some of the content. And additionally, it takes in some of the sensor data as well. So then it uses that sensor data to correlate to, if this cyber anomaly has had a physical impact on the grid. So this is primarily a data-driven machine learning approach using unsupervised machine learning. So a lot of the training data comes when there's no anomalous activity on the grid, and then it runs during the normal grid operations. Next, the resilience metrics here that we use, we call it adaptive capacity. And it's really trying to look at what is the headroom that you have on an aggregated set of components. So if you have various components and it looks at that in terms of real and reactive power. So how much additional real and reactive power can I push through this small section of the grid? And it quantifies that, and you can plot it in these 3D plots. So the z-axis is time, and then you have real and reactive power on the x and y axes. When you're looking at this from a dynamic perspective as well, you can see how a disturbance will affect the grid over time. So the bigger this figure is, as long as all the loads are being served, the better, because the bigger this figure, the more adaptive capacity you have. And as disturbances or changes in the load occur, that adaptive capacity can reduce with time. And the less amount of adaptive capacity you have, the less margin to maneuver or to reconfigure your grid you will have to adapt to future disturbances. This next piece is CPODM, so Cyber Physical Outage Data Management System. It really describes how all these tools come together and how the data is driven towards our visualization system. So I'll just walk through this slide, and it's a little bit more complex, so I'll go into a little bit more detail than what's shown here, but we have a real-time Opal RT system, which talks to Schweitzer electronic equipment. So our power grid model resides on here, and some of the Schweitzer electronic equipment does some control on the power grid. And all this data is sent to a switch. So this switch then parses the data out to SciStar, our cyber sensor that I discussed earlier, and which is then also filtered to the Kafka database. The switch also sends the physical data to the Kafka database. And this is where there's a little bit more detail going on than is shown here, but the Kafka database also sends the physical data to the resilience metrics, where that's calculated and stored back in the database. And then it also sends data out to the Viz engine or the visualization system that I'll go over in a little bit sooner. Two other components, the Neo4j. This was meant to be a low fidelity digital twin of the system in a sense. It uses graph theoretics to map out the connections between the physical system and the cyber system. So if you're having some physical anomaly occurring, you can kind of look at, what cyber components are connected to that physical, and then better assess, where this cyber attack might be coming from, or if it's connected to some cyber anomaly that was detected. And then the InfluxDB is just a data storage in case the Kafka database goes down, so you can use this as a backup. Here's just a general overview of the Viz engine, and then we'll drill down into some of the different screens that we have developed. So you have your main Viz engine, and there's the different screens there for the grid operators, the cyber defenders, and the power management folks. So that's what this next one is trying to show. When you have an anomaly or some occurrence occur on the grid or some adverse effect, what you can do is we've developed these cyber physical playbooks. So these cyber physical playbooks, they are modeled after what's actually done in the cyber world because they have cyber playbooks. And so we wanted to expand that to physical and cyber physical events. That data is then fed to the operator who can follow through these flowchart diagrams and make the appropriate action into the control room. One of the things that's really important when you're designing visualization and visualization tools is that it's easy, it's intuitive, and it doesn't create more work for the user. So we tried to keep that all in mind when we were designing this. And we had looked at some other visualization methods that were used by other utilities. So we have different role-based screens. The thing that we like about this method is since it's all built into one package, it can provide a common communication tool. Since the power engineers can access the cyber, though we don't really expect them to do so, but it can provide a common language for them to use. And part of that is focused on these little triangles, which I will get into later. So the Cypher triad, as what we call it, it has three different components. It has the cyber component, a physical component, and a resilience component. And we modeled this after a stoplight, so red is bad, green is good, essentially. Tried to make it very easy and intuitive. So no matter if you're a cyber defender or if you're a power grid operator, you'll probably be seeing these triangles there, and it's going to provide an indication of you probably need to call the other team to start collaborating if necessary. And each of the definitions for what's green or yellow it's a little bit different for each area, but we have the definitions here as well. Here's an example of the main overview. For a lot of the studies we did, we used the IEEE 33 bus system. And you can see here these groupings. These are what we would consider our aggregated system resources, so our ASR units, how we group them. And depending on what's going on in the grid, these colors on these triangles will change. This is a drill down menu for a cyber defender if they're looking at a subsection of this grid. So this looks like it's ASR 5 right there. And then they have a lot of their cyber tools down here. So this would be like a bingo chart that tells them what packets are coming from where and where they're going to. And then some of our cyber sensors indication is there a physical anomaly occurring, or if there's a cyber anomaly occurring, which would be below that, the cyber one. We also have a manager menu, which kind of goes into what tasks need to be done and what the duration of those tasks, what resources are available to get those tasks done. This is an initial attempt at our playbooks. It's fairly rudimentary, but we're hoping to make it more interactive with a flowchart diagram. So you'd have the different steps here, the timestamps, you know, the different approvals for the managers that you need to go through, notes in the description. This is kind of the direction that we want to move with that, where it's a more interactive flowchart diagram, and that's some work we'll be finishing up this end of this month to run some new scenarios and do some new tests, and then try and integrate this additional functionality into it, where the physical defenders or the physical engineers, they would get one version of this that correlates to also a cyber one, and then the cyber defenders would also get their version of it, and they can collaborate together better as they go through the different steps and make changes on it. So in summary, we've developed a variety of different tools in STAR, which attempts to quantify the physical health of the system, quantifies it locally, and then it also tries to quantify it globally. It also has some flexibility in that it allows you to weight different areas of the grid. So if you want to reflect, you know, this part of the grid's hurting more, that's going to affect the global health more so. You have that flexibility. We have SciStar, which is a unsupervised machine learning data-driven approach for detecting cyber anomalies. And then it also takes in some of the physical sensor data to ensure that there's some correlation there. We have the CP-ODM, which is the outage data management system that really takes everything together, aggregates the data, does some analysis, and then spits it out to the visualization system. We also have the resilience metrics that I discussed. And then lastly, I gave you a brief overview of the VisEngine metric or the VisEngine visualization tool that we developed. Some of this technology is in the process of being licensed out, so we're very excited about that. And at this point, I'd like to open it up if you guys have any questions.
Yeah, thank you so much, Bjorn, for the nice presentation. Is there any question? We can have one question from the audience and one from the virtual attendees. Any question from the audience?
Can you please tell me about more Neo4j?
Yeah, sure. Neo4j, that is part of Virginia Commonwealth University, some of the stuff that they're helping work on with this project. But essentially, it's taking a graph database and it's linking all the relationships that you have in the physical system, and then how all those relationships also tie into the cyber system. So you can think of maybe there's two graph databases. One is the physical, and then one is the cyber, and then how they're all interconnecting to each other. So when there is a physical anomaly that occurs, we can assess that database and see where the different relationships are into the cyber system, and if there's a cyber anomaly. And so we can help draw the connection about, maybe what the attack vector might have been, or where their pivot points might have been, in the system. So does that kind of answer your question? Okay. Yeah.
We can have one last question from the virtual audience. So we have here, could you speak a little bit more on how the local and global health metrics are computed?
Yeah, sure. I can try and describe that a little bit better. So it's a deviation-based health metric. Exactly the math behind how they compute the single lambda from deviations of voltage and deviations of power flow, I'm not exactly sure, but those are the two factors that go into computing that. I'm going to go back up to the slide to help me describe it better. But then, essentially you have, once you compute your lambdas from your alpha and your beta, which is your voltage deviation and your power flow deviation, These would go into summation that would come out and compute your global health factor. Then you would have other things that would be like different multipliers on top of that. So you'd have your supply factor, which is shown in here. So, how much of this this lambda for this local area, how much can it supply its own power? If it can supply all of its own power, that's a big bonus. Then, what's not shown in this graphic is, dependency health factors. Maybe this lambda D1 is dependent on lambda D2 for power. So then that would kind of detract, from it, depending on how well lambda D2 is doing. So if lambda D2 is, doing poorly and lambda D1 is doing well, or depends on lambda D2, then you're going to have, that's going to detract from the health of D1. Just fast forwarding just to give you an example of it. So, ASR5 is dependent on ASR1. So if we have a problem in ASR1, you're going to have a problem in ASR5 and all the rest of these. Or, ASR3 is dependent on ASR2. So if you have a problem here, it's possible you could reconfigure the grid. So you could close this line here to redirect power. But, if you have problems with ASR2 and 6, you might be out of luck. And then so that's going to really affect the health of ASR2. And so when they take all these dependencies, these multipliers into that lambda, you sum them up, and then that's your global health.
Thank you so much. Let's thank one more our speaker.